Hey, what's up, guys? Chung here again. So today, let's continue on this minimum area rectangle problem number 2 here. So I believe a few days back, we discussed about the minimum area rectangle number 1. So now this time, let's take a look number 2. And if you guys still remember, in the number 1, everything else are the same. Okay, the only difference is in the number 1 is the all the lines that consist of a rectangle has to be either vertical or horizontal. Okay, so in that problem, it's a little bit easier in my opinion because in that problem, I believe we use two solutions. The first one is we fix 2 points here. We fix 2 points, and then with these 2 points, okay, P1 and P3, we can easily find the P2 and P4. Okay, so that's the first approach we used, and second approach was remembering all the vertical lines here. Okay, basically we were using like a hash table to store all the vertical lines, and it's like with all these vertical lines, also for each of the vertical lines, we also use another hash table to store its latest x coordinates so that we can scan it, right? That's the two approach here. That's sorry, that was the were the two approach for the first rectangle problem. But here, since the rectangle can be rotated, right, in either direction. So mm, so we cannot like use the 2 points, right, to fix that. Basically, our first approach for this problem is that we have to find still okay we find the first uh two points, and then we'll try to use the the Pythagoras theorem to find the third one, to find the third point, okay? And with the third point, then it's easy. We can find the the fourth point. I mean, I can show you guys how can we find the fourth point by using 3 points later on. But let's try to find the 3 points first. Okay, cool. Okay, so I think first I'm going to define like helper functions, to help me calculate the distance, okay, between 2 points, like P1 and P2 here. And basically the distance I'm calculating here is the P1 dot 0, okay, minus P2 P2 0, the difference of x, and I'm gonna do a power of 2 plus same thing P1 dot 1 minus P2 1, the second element of P2 still, and then I'm gonna do a return here, return D. Okay, that's pretty straightforward. And then the first thing is just a brute force. Basically we iter through all the points, okay, and we find the 2 points first, and then we then the third point, and then by using the first 3 points we can find the fourth point. Okay, so let's see. So the answer is this. Okay, system dot maximum, right? And then P1. Okay, in P1 in points. Okay, and then for P2 in points. Okay. Uh, yeah, let's see. Actually, maybe we can use that scene technique to reduce the amount of points we are never mind. So let me finish this one first. Let me finish the real brute force version here. So basically, if P1 equals to P2, okay, we simply continue, okay, because we don't want to find, we need 4 different points, okay. So since now we have 2 points, now let's find the third point, okay. If P3 is in for P3 in points. So first, if P1 equals to P3 or uh, P2 is equal to P3, okay. We continue. Else what? How can we know if the third point is the point we need? We need to know. That's why we need to use the Pythagoras theorem, right? We need to know if those two, the distance between P1 and P2, basically if the a square plus b square equals to c square. That's that's when we can tell. Okay, so we have a 90-degree angle. Okay, between the P1, P2, and P2, P3. Okay, so basically if the distance right between the P1 and P2 plus right distance of the P2 P3 it's not equal to the distance, okay, it's not equal to the distance P1 and P3. Okay, so if that's the case, we also continue, right? Basically that's this P3 is not the node we the third point we are looking for here. And okay, so now if the third point is there, okay, if we have find the third point, now here comes the trick. So how can we find the fourth point? So here's the trick. Basically, you know, the x1, basically the x1 uh plus x3 equals to the x2 plus x4, and y1 plus y3 equals to the y2 plus y4. You know, let's say there are like 4 points here. Okay, there's a 1, 2, 3, and 4. So no matter how we rotate this rectangle, these two formulas always stays true. You can try it, right? I mean, this is 1, 2, 3, and 4. Okay, in this case, it's like 1, 2, 3, and 4. Yeah, I think there is like a formula, or you can look something up. Let me try to find these things here for you guys. Okay, so I found this website here. Let me drag it to here. Okay, so basically this is the website, I mean, where you can basically you can play around with it so that you can understand why that equation always 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 true. It's always true. Okay, you can drag it, right? Drag it whatever you want, but and there's like some more explanation on this one to explain the relationship between those 2 points here, between those 4 points, not 2 points, sorry. Cool. Coming back here, right? Since we have this formula here, right? We have this like equation. Then with 3 points find, we can simply find the fourth point. Okay. Now the x4 will be what? Will be the p1, okay, 0 plus p3 0 minus p2 0. Okay. Same thing for the y4, right? So for the y4 here, p1 1, p3 1, p2 1. Okay. So now we just need to look for if x4 and y4 is in the points. Okay. Uh, if it's in the points, then we simply do a area, right? We simply do a area equals to what? We do a we can utilize this method, but the only difference, sorry. So we can basically the two side, right? It's gonna be the distance between the P1 and P2, okay, times distance of the P2 dot P3. Yeah, P2, P3. But remember, we have a square result, right? That's why we have to do we have to use this squirt. I mean, so we have to use this square foot method to get the actual length. Okay, square foot here. Okay, and then we simply update, right? Do a minimum of update answer dot area. Okay, and then we can simply return the answer here. Answer, of course, if the answer is smaller than the system dot maximum, right? Else, else zero. Yeah, I think this should just work. Okay, let's try to run this. Hmm. No. Mm, let's see. Uh, P3 if P1, P2, P2, P3. Continue. Mm, maybe here, maybe the if area is greater than zero, then we update. Hmm. Okay, let's see. Yeah, I think I know what went wrong. So here I'm using like a set, but in the points here it's a list, not a set. So what we need to do here, we have to convert this point to a point set. Not only we can just use this set, but also when we are looking for those those points, right? We're looking for those points. We can sorry, when we're doing this fourth point, look up here. We don't have to scan the whole list. Since we're converting to a set, then it's gonna be O1. So we're gonna improve that, improve our runtime here. Basically here, P0, okay, dot P1 for P in points. Okay, here point set and then point set. Okay, so I think here we can remove these things here. Okay, let's try to run it again. At least the test case passed. Submit. You know, I believe these things it will TLE because uh, oops, no, it didn't TLE. Okay, surprise. Okay, I thought it will TLE because the time complexity it's like it's gonna be a what n square, right? Basically, we have a first loop here, second loop, and then the third loop. I thought it would TLE, but it barely passed. Okay, I think one of the mm, one of the improvements we can do is we can do a scene like just like what we did in the first rectangle problem, you know. So every time when we have a point here, okay, we add this one to the scene, okay, like this, you know. like scene dot add uh, add p1, okay, and here we just do a scene, okay, yeah, so that we incrementally we slowly increasing the size of the scene here, okay. I think this should also work. Let's try it. Okay, submit. Yeah, see, it's much faster, you know, but still the percentage didn't change much, but the runtime did decrease a lot. So basically, you know, what we're doing here, instead of course, for the first loop, we have to loop through all the points. But for the second and the third loop here, I mean, we don't have to loop through everything, right? Because we just need to know like what we just need to loop the points that we have seen before. We had seen before. That's why I'm using this scene set, right, to improve this. Because the first time we only have one, two, three, and four, so not so it's not just strictly n, n it's, it's not strictly n to the power of three. Okay, it's maybe it's n uh to the power of 2.5 or something like that. You know, basically by using the scene here, we can improve the performance by a lot. Okay, cool. So I think that's pretty much the first approach here. I mean, it's kind of straightforward, right? The only thing you guys need to understand basically two things. First, you guys need to know the Pythagoras theorem so that we can use this one to find our third point. And here, basically find third point. And then more importantly, that's how we find the fourth point. Okay. And once we have all fourth point, all it's left is just to calculate the area and then compare with the answer. Cool. So that's the first approach. Okay. It's still like n cubed, right? So even though it's like perform better than n cubed, but I believe it's still bounded to n cubed. Okay. So let's try another way. Let's try another solution here. Okay. Mm. Okay. So another solution is it's by using the center point of those two diagonals. If you guys remember the rectangle problem one, it's like always like this, right? So basically, there's only one possibilities of the two diagonals, right? That's the only possibilities of those two diagonals. But with this like kind of the problem number two here, those two diagonals, I mean, they can be rotated basically as long as the center point doesn't change. Okay, those two diagonals can rotate to any direction. Okay, so they can rotate like this, I mean, right? And they can also rotate somewhere here. Okay, so then basically this is one of the rectangle. Okay, and this is also one of the rectangle. Basically there's going to be unlimited, like infinite number of squares that's these two these two diagonals can be formed. Okay, so that's how we are going to find our 4 points here. Yeah. So the way we're going to do here is we're gonna use like also a hash set, right? We're gonna use a hash set to find to maintain, right? To maintain the all to maintain each of the diagonals. That's every 2 points can form. Okay, basically we have like this list of points, right? So basically each 2 points can form like essentially can form a diagonal. Okay, basically, so that's why we're gonna loop through all the combinations of the 2 points, and with each 2 points, we can find the basically the length of diagonals. Okay, and then we can also find the point, right? The middle point of the diagonal. That's why we're gonna use those two things as a key, right? To as a key to store each of the diagonal lines here, and then. mm, Yeah, and then once we have the hash set map, then we can loop through the hash set map, right? We will be finding, so basically we're trying to find uh, the two lines, the two diagonal lines, which who has the same center point, middle point, and the same length. Then we know, okay, so the points for those two diagonals are one of the candidates we need to form like rectangles. Okay. So let's try that. Basically, uh, still we need this like we need these things here. We need this distance to help us define the distance, and then uh, we need a diagonal, diagonals, uh, default default dictionary. Okay, so the list. So why I'm using a list here because with the same center point like and also the same length, right? We might have different pairs. Okay, we may have different pairs of the nodes here. For example, here, if we also have a like nodes here, like somewhere here, 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 and here, right? Then with these two things, I believe those two pairs of nodes will have the same center point and the same length of diagonals. So with the same center point, and the same length of the diagonals of the points pair, we're gonna store them into the same list here so that later on we can simply loop through the pairs with the same key. Okay. So for uh, I in range, so we're gonna have like a length of the points here. For j in range sorry, I plus 1 to n. Okay, that's how we iterate all the combinations, all the two combinations of the 2 points. Okay, uh, so p1 equals to points I. Okay, and then p2 equals to points j. Okay. Uh, so the center x, right? The center x equals to the p1. What's the center x? The center x is p1 0 plus p2 0 and divided by 2. Okay, so we need a parenthesis here. Okay, same thing for the center y here, right? So for center y, We have a P1 1 plus P2 1 divided by 2. Okay. Now the distance, right, or the length. We can call it the length. The length is the distance, basic distance between the P1 and P2. Okay. And we're using, remember this length is like the power, the square of the actual length, but doesn't really matter. We just need a like unique value that can be a part of the key. So it doesn't really matter if you do a square foot or like just use this like the square version. The yeah. Mm, now we have a diagonals. Okay, so now we have all the keys we need. The first one is the center x, the x and y, and then what? The length. Okay, that's the three keys. Okay, and then we do a append, right? Append to what? P1 and P2. Okay, so that's how we maintain the hash set of the diagonals. As long as, as long as those three parts are the same, then we know, okay, so those all the points, right? All the points will be able to form like a rectangle because they have the same diagonals with the same length and the same center position. Now we just simply need to iter through all the all the points with the same key. Okay, so answer equals to this max size. Okay, for key, I'm going to use the key here in diagonals. Okay, uh, so with the key we have the uh, points pair list, right? Equals to the diagonals key. So here is storing all the pairs with the same diagonal key, right? And then we're gonna have like a length here, like n1 equals to the length. So why we're doing this thing here? Because we only will continue if the n1 is greater than 1, right? So why we're doing this check? Because let's say if there's only one pair, with the same diagonal key here, it means that there's only P1 and P2 here, right? So there aren't any there isn't any other points that can help the P1 and P2 to form the rectangle here. That's why we're going to check if there's only one pair, then there's no way we can form like a rectangle. Okay. Okay, so if the pair number is greater than 1, then we know, okay, we can try all the possible pairs. Okay. So for I in range n1, okay, and for j in range like I plus 1 dot n1, okay. Now we have all the points here. We have p1 equals to what? This thing, uh, I I0, okay, and we have p2, p3, p4, okay. P1, p2 is this, I1, p3 is j0, and p4 is j1. Okay, so basically this is a p1, p2, and this is a p3 and p4. Okay, so now what's the area here, right? So the area is it's kind of obvious, right? The area is like the square foot of the distance from P1 to P3 times square foot of the distance of the P1 and P4. Okay, then same thing, answer equals to the minimum of answer dot area. Okay, and then uh, same return here. Okay, yeah, run, submit. Cool. See, this one is much faster. Okay, it's much faster. It's even, you know, the worst case scenario. I mean, this thing is should be like at least it's an n square, right? Yeah, I think so. And for this solution, it's n square because for to calculate the diagonals hash set here, we loop through all the nodes here, all the points. So that's n square, and then here we're looping through all the keys here. I mean, here the key here is much smaller. Seems like the test cases they're given here has a lot of rectangles, and then actually the size of the diagonals it will be much smaller. And this here is definitely uh, smaller than n square. Yeah, and so this one is the most expensive part. Yeah. Cool. So basically, that's the second solution here. I know this video is kind of long and probably not that clearly explained, but I just want to show you guys like the, the uh, two different type of the rectangle problem. The first one is the it's not the rotated version. The second one is the rotated version. So for the rotated version, there are like two ways you can find those 4 points. Okay, the first one is find the points one by one. Find the first one, second one, and then use the Pythagoras theorem to find the third point, and then use this like the relationships to find the fourth point, which is the n cubed time complexity. And the second one is it's much faster because we pre-built the diagonals. Basically, we use the diagonal lines to find to fix the 2 points, and with the same diagonal lines, then we know okay those two pairs can form like a rectangle, and which is much faster. Cool, guys. I think that's it for this problem. Yeah. Thank you so much for watching the video and stay tuned, guys. See you soon. Bye bye.